Level 1 and Level 2 chemical equilibrium problems. In this particular problem, the decomposition of sulfur trioxide to give us the sulfur dioxide and the oxygen. They're giving us the size of the container, 4 liters. They're giving us one initial condition, that is for the reactant, the SO3, that we have 0.6 moles. And we're given one equilibrium condition when the rate of the forward equals rate of the reverse, and that is for the oxygen. And what they'd like us to calculate is the equilibrium constant Kc from the mass action expression. So to help us solve this problem, let's place into the equilibrium chart everything that we know initially and at equilibrium, so that we can find all equilibrium values and ultimately, by using the mass action, calculate the equilibrium constant Kc. In this problem, we were given the one initial value, that was for the reactant, the SO3, and the one equilibrium value for the O2. Notice I went ahead and placed the moles over the liters, because moles per liter is molarity, and when you place values into your mass action, things have to be in molarity. So if we go ahead and divide the moles per liter, we'll get the molarity for the one initial and the one equilibrium value. For the other initial values that were not provided, you have to assume that you do not have any. They would actually provide you with a number if they wanted it for the initial value. So if they give you at least one initial value and don't state anything else about the other initial values, you have to assume that they're 0. So we can go ahead and place zeros in initially for what was not provided. And now we have to talk about the changes that would undergo to go from the oxygen initially not having any, the 0, at equilibrium when the rate of the forward equals rate of the reverse, to having 0.03. Obviously, to go from having nothing to having 0.03, we had to add 0.03. Now, if you're adding for one product, in this case the oxygen, you're going to have to be adding for the other product simultaneously, the SO2. You can't make one product without making the other one. Now, how do you know how much SO2 is going to be made? Well, we can look at the ratio between the two products in the balance equation. It's a 2-to-1 ratio, so it says we make twice as much SO2 as we do the oxygen. So if you double 0.03, then obviously the amount of SO2 that would have been made simultaneously would be 0.06. So we're going to add 0.06, double the amount. Why did I add double the amount? Well, I'm looking at the coefficients in the balance equation. It is a 2-to-1 ratio. So if we go ahead and add the 0 and the 0.06, at equilibrium we have 0.06. Now, you can't create something out of nothing. If you're adding on the product side, you must be taking away on the reactant side. How much are we going to take away? Well, it doesn't matter if you actually use the SO2 value, the 0.06, or the O2 value, the 0.03. Either one of these will give you how much SO3 to subtract. Where do we need to focus our attention? On the coefficients that balance the equation. If we take the 0.06 for the SO2, let's look at the ratio. There's a 2 in front of the SO2, and there's a 2 in front of the SO3. It's a 2-to-2 ratio, or a 1-to-1 ratio, which says that if we add 0.06, then we should be able to subtract 0.06. What if you focused your attention on the 0.03? Would you still know to subtract 0.06? Well, if you focus your attention on the balanced equation, you would also see that in front of the oxygen there's a 1, and in front of the SO3 there's a 2. It's a 2-to-1 ratio, so you need to subtract twice the amount. So whether you focus your attention on the SO2 or the O2, both of these values tell you to subtract 0.06. So by subtracting 0.15 minus the 0.06, at equilibrium we have 0.09. Now that we have all the equilibrium values, we're now ready to plug this into our mass action expression. If you recall, the mass action expression is nothing more than the ratio of the concentrations in molarity of the products over the reactants, with the coefficients that balance the equation becoming exponents in the mass action. So let's take these equilibrium values and let's write a mass action for this balanced chemical equation and calculate our equilibrium constant. So we take the equilibrium values from the previous screen, Notice I've written my mass action. I have my products on top, the SO2 squared. Why squared? Because this coefficient right here becomes the exponent. The oxygen is the second product, and the SO3 is our reactant. It goes on bottom. Why the 2 here? Because of the 2 in the balanced equation. So now if I plug in my equilibrium values into this mass action and complete the math, we'll be able to calculate our equilibrium constant. This equilibrium constant is less than 1, which simply says that equilibrium favors the reactant side. Remember, at equilibrium, it is when the rate of the forward equals the rate of the reverse. However, equilibrium can favor one side or the other. It can favor the reactant or the product side. A K value less than 1 says that this favors the product side, favors the reactant side. Whenever you get ready to write a mass action, one last thing that I'd like to point out is notice that all reactants and products are in the gaseous state. If things are not in the gaseous or the aqueous state, if they're a liquid or a solid, they cannot be included in the mass action. So do not include liquids and solids in your mass action. The second problem that we'll take a look at is a little bit easier problem. We'll refer to this as a level 1 problem. Why is this one easier? Well, all equilibrium values are provided. You do not have to use your equilibrium chart to figure out what values you're going to have at equilibrium. They are provided. Notice the quantity is given in moles and the size of the container, so you're going to be able to calculate the molarity of everything at equilibrium. Plug it into your mass action, products over reactants, remembering to raise to the coefficients of the balanced equation. So if we go ahead and write down what we know, within our equilibrium chart we have everything at equilibrium. So this is the easiest type problem you can have. And all you have to do is plug these values into your mass action expression. So we go ahead and divide the quantity by the size of the container, the 2 liters. We'll have our equilibrium molarities that we can plug into our mass action. So if we write our mass action, products over reactants, all the coefficients here are 1, so everything's raised to the understood 1 power in the mass action. Plug in our equilibrium values and we'll be able to calculate Kc. Notice once again that our K value is less than 1, which simply means that equilibrium favors the reactant side.